So we're going to be talking about atoms, molecules, and ions. So the main three things we're going to learn is the composition of the atom and how the composition was discovered. We will be learning the periodic table organization, and we'll also be learning how to do naming. So naming is a huge skill that we learn in chemistry. All right, so before we start, we need to talk about these fundamental laws. These fundamental laws, there's three of them that are integral to any discovery of matter, any science we have to do with matter. So the first one is the law of conservation of mass. And I'll go through them kind of quickly because they are boring, honestly. So the law of conservation of mass is the first one. So basically it states that mass can neither be created or destroyed in a chemical reaction. So if you have a closed system, let's say a beaker, and you put in NaCl into the beaker, or NaNCl separately, and let's say they react to make NaCl. If you have 5 grams of Na and 5 grams of Cl, this is not the actual ratios that they react with, but theoretically, if you react them, you should get 10 grams of your product, or 10 grams of stuff at the end of the reaction. So if it's a closed system, nothing is going to escape or enter. It should be exactly 10 grams. So you're not losing mass. And this kind of ties into this theory that the universe has constant mass. And whatever that mass is, no one knows, but it's a constant mass. There's no matter being added or subtracted from the universe at any given time. Quantum physics kind of debates this with this parallel universe theory that you can go in between universes and it gets really complicated from there. But our basic laws of chemistry state that mass is conserved and cannot be randomly disappear. So that's very important. Okay, the next one is the law of definite proportions. So this one and the next one might seem like, oh, no, duh, of course that makes sense. But it's important to go over. And it states that any given compound, let's say H2O, it only exists as H2O. You can't have water molecules that are H3O or H2O2, because those are fundamentally different compounds. So if they do have a different ratio of atom A to atom B, or element A to element B, that's a different compound. So for definite proportions, it says that every sample of water, no matter where you get it from, has a definite proportion of 2 hydrogens to 1 oxygen. That is a definitive thing. So not too complicated, but you have to say that exists. And I see a lot of you scrambling notes. You don't have to write every word. If this is going to be recorded, you can see it over and over again. You can read it online, but just know that all the compounds from either source A or source B are all the same proportion, if they're the same compound. There you go. All right, so this is John Dalton. He's sexy, right? So he invented a lot. So he thought of a lot. So he has his own atomic theory. So we'll talk about that in a minute. He has his own law of multiple proportions, which we'll talk about right now. So the multiple proportion law is a little bit more complicated, and it's got weird wording. So we got to try to understand it together. But it says when 2 elements form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element, doesn't matter which one, it could be either or, can always be reduced to a small whole number. Okay, what the hell does that mean? So let's do an example. Let's say, where's the example? It's not, okay, I don't think we have an example, but I'll just talk about it. So let's say we have carbon and oxygen, right? So carbon and oxygen, 2 elements, they form 2 different compounds. Actually more than that, but 2 common ones. CO, carbon monoxide, will kill you, and also CO2, which you need to live. So carbon and oxygen form those 2 compounds. So the first compound, carbon and oxygen, if you take the molar masses, which we didn't learn today, but we didn't learn yet, but we will touch on today. If we take the molar mass of carbon, which is 12, and we take it for oxygen and we divide the 2. We try to figure out the mass ratio of carbon to oxygen. Take that mass ratio, Then we do the same thing for carbon dioxide. We take the mass ratio. If we divide those two mass ratios together, we will every single time get a whole number. So some of you can do that on paper, and we'll see in the next slide an example of that. You might think, okay, it makes sense, whatever, that I guess so. What does that mean? So the reason why it's important is because it states that all of the atoms or all the elements that make element A and element B that make different compounds 1, 2, and 3, that they have definitive mass ratios. That if you add more of element B, for example, the mass ratio will change by a whole number. So by a whole number multiplicity. So it'd either be divided by 2, multiplied by 2, if you add another element B. So that's important. And also, it also proves the rule that you can't have half an atom, because that's not a valid compound. There's no such thing as half an atom. So yeah, is there a question? Oh, it's okay. Don't worry about it. I got your email. Did you send me an email? I think that was you. Yeah, I got the email. Okay. So, does that make sense? Yeah, kind of, sort of. All right, example time. All right, so here are several compounds with nitrogen and oxygen. It's actually 3. So compound A, the mass of nitrogen that combines with 1 gram of oxygen. So this is the mass ratio of nitrogen to oxygen for 3 separate compounds. Compound A, the ratio is for every 1.75 grams of nitrogen, there's 1 gram of oxygen, and then B and C. So which ones out of compound A, B, and C has the most nitrogen atoms, you think? A. Yeah, A, exactly. Everyone's kind of like, I don't know. I don't want to say the wrong thing. So it's A, good, because it has the most mass of nitrogen per 1 gram of oxygen. So it's got to have the most nitrogen in it, right? And then this one has the second most, and then compound C has the third most. So I'm pointing at the board, but there's only 4 of you in the class. Meanwhile, nobody can see it online. So what we can figure out is that if we take those ratios and divide them by each other, we'll take the first ratio of A divided by the ratio of B, you get a whole number. And somebody would be like, oh, if you flip them, you get a decimal. There goes your law. Well, no, it's still a reducible fraction that you could be. So then you do the same thing for B and C, and you do the same thing for A and C, and you can get a whole number. So that's the law of multiple proportions in action. Okay, question time. So according to the law of definite proportions, which one of these is true? So A, if the same 2 elements form 2 different compounds, they do so in the same ratio. Does that sound right to you? No, because they form 2 different compounds, they have to be in different ratios. If they're in the same ratio, well, they're the same compound. So that can't be right. It's not possible for the same 2 elements to form more than 1 compound. That's BS to me. That's not right. C, the ratio of the masses of the elements in a compound is always the same. What do you think? The ratio of the masses of the elements in a compound is always the same. Yeah, makes sense to me. Yeah. And so D, let's see why it's false. Total mass after a chemical change is always the same. Is the same as before the change. That's true, but it's not the law of definite proportions. Okay, cool, good. So let's get to Dalton's atomic theory. So Dalton had this atomic theory. Yeah, he did. And basically what he said, there was 4, well, depending on where you look, but there's 4 main postulates. I think this book uses 4. So the first one, and not all of them are true. So keep that in mind. I hate when like some professors do like they say something and then like you're learning about it, oh wow, it's interesting. And then at the end they're like, yeah, so that was proved wrong. And then you're like, I just learned it. What the hell? So I'll come out up front and say it that not all of these are true, and I'll explain why as we go through them. So the first one, each element is made up of tiny particles called atoms. Duh, that's true, right? Second one, atoms of a given element are identical. Is that true? Anybody know? So I'm asking because it's not true. It's not.
But like all the atoms of iron.
Not,
I don't know the difference. Yeah.
What's the difference? Do you know the difference?
Well, no, I mean like carbon has, there's like carbon 12, carbon.
Yes. What are those called? Isotopes, exactly. So all of the atoms of a given element are not identical. And for example, like you use with iron, they have other variables too, like charge.
Yeah.
Some of them have +2 charge, +3 charge. Some of them are neutral. So you could have different states of them. So yeah, they're not exactly identical. But back in the 1800s, they had no way of detecting isotopes. So we're going to talk about isotopes today. But something that's interesting about them is basically what an isotope is you can have, like Harrison said, carbon 12, 13, and 14. Those have the same number of protons, the same number of electrons, but a different number of neutrons. Therefore, their mass is different. Their mass is 12, 13, and 14. Now, in a chemical reaction, there is absolutely no detectable difference between isotopes. So they do behave differently, and we figured out as scientists how they behave, not me, but like everyone before me figured out how they behave differently. So you can detect isotopes with mass spec. That's a really powerful technique, or NMR. So these isotopes, in simple chemical reactions that they had in the 1800s and 1900s, they couldn't figure out the difference. And since atoms are so small that there's no way of detecting the mass difference of carbon 12 to carbon 13, because you couldn't isolate one single atom. And so in case you're wondering, the way it works for carbon 12, 13, and 14, and it's a thing you should know if you're getting into, let's say, chemical engineering or something, that 98% of all carbon atoms are carbon 12. About 1% is carbon 13, or a little bit more than 1% is carbon 13. And like 0.4 or 0.5% is carbon 14. So not many. And then if you take the weighted average of all of those masses, you get 12.011. And that 12.011 is the molar mass of carbon on the periodic table. So we'll see those calculations in action, but that's exactly how it works, where you take the weighted average of all of the different naturally occurring isotopes and take the weighted average based on their abundance percentages to get the average atomic mass. And it took a lot of work to figure out those abundance percentages, because you have to get naturally occurring samples from all over the world, put them through a mass spectrometer, and then see the ratios, see how they correlate, and then average them all out, and then make these rules for our periodic table. So it took a lot of work to do that. And you would do that for every element. Okay, so let's go on to the third and fourth postulate. So the third one, chemical compounds are formed when atoms of different elements combine with each other. That's true, right? Because we learned that compounds are combinations of chemically combined, I was about to say compound. I wish that was the word. Chemically combined different elements. That's true. Now the fourth one, chemical reactions involve reorganization of atoms. That's true. But then the last part, atoms themselves are not changed in the chemical reaction. Is this one true? Any idea? No? Okay. So most of the time it's true. But when you deal with radiation and radioactivity, that's where atoms could actually change into other elements. So nuclear fission, nuclear fusion, for example. So you can have the emission of particles from the nucleus. So basically what radioactivity is, and we're going to dabble on it today. So radiation is when the nucleus explodes. That's basically it. You have an unstable nuclei. It builds up a lot of pressure of energy inside the nucleus. So the protons and neutrons, or lack of neutrons, is causing a buildup of pressure or buildup of force and energy inside the nucleus. Eventually, that force overtakes the force of the nuclear, it's called the nuclear force actually, that holds the nucleus in place. Therefore, the nucleus explodes and things come out. Protons, neutrons can come out. So therefore, in a radioactive decay is an example of a chemical reaction. In that case, you have particles leaving the atom, and the atom actually changes from, let's say, uranium to to something else. I don't know, palladium, sure, whatever. Lead even. So if enough stuff comes out. So that's crazy. Okay, so this leads us into atomic masses. So Dalton also prepared the first, I didn't know that. The first, I forgot about that actually. So he also prepared the first table of atomic masses. It's pretty cool. And they are on the periodic table. So you don't have to write this down. It's just, we'll see it in action. Yeah, and also, yeah, he was more of a theoretical guy. So like many of them were proved wrong because of his incorrect assumptions about the formulas, because they had no way of doing this like the early 1800s. All right, so now we're going to go over 3 really key experiments, but we're not going to dwell on them too much. So if you don't understand like how Millikan's oil drop experiment works, which is the next one, and it's kind of difficult to understand, there's not going to be like 50 questions on it on the exam. There may be one homework question, but not really on the test. So these tests are going to be based on your understanding of the chemical concepts, not really a history lesson. So whether you can do the calculations, whether you understand the periodic table, how it works, stuff like that. So anyway, so in order to, so Dalton came first and he was like, all right, we have these basic chemical laws that I developed. And these other scientists came and like, all right, we know about these really small particles called atoms. Now we need to know what they're made of or what's their properties. Because up to this point, they didn't know their properties. They know that, all right, they're neutral, some of them. Most of them are neutral, right? Because if you touch a desk, you're not going to get zapped. So they're neutral. So they figured, all right, it's probably just like a particle. Nothing special, just a particle. That was the theory. But so then what they're going to do is they're going to do different experiments to try to prove or disprove theories that are bouncing around at the time. And the first one of these was J.J. Thomson did his cathode ray tube experiment. So what a cathode ray tube is, it's just a stream of electrons. So he put the stream of electrons through a tube and he put 2 electrodes in the end of the tube. One of the electrodes was negative. One of the electrodes was positive. I'll move my cursor over. Here we go. This electrode was negative. This electrode was positive. And he applied an electric field. So, and the positive end was here, negative end was here. So generally, if you shoot electrons, they always come from the negative end and they're going to go towards the positive end. But if you add another electric field, you can bend the path of those electrons. Or at this, they didn't know it was electrons. They just thought if it's positive, it'll go one way. If it's negative, it'll go the other way. So they experimentally measured that they go towards the positive end. Therefore, it's positive, or it's negative. So since they're repelling the negative end and going towards the positive end of the electric field, they have to be negatively charged. So they're like, all right, there's something that's negatively charged. So that means that because they have the preconceived idea, which is true, that most of the atoms are neutral, that something also had to be positively charged. So J.J. Thomson kind of proved the electron. So he assumed that, all right, because of this experiment, all atoms must contain electrons. I'm paraphrasing, of course. And the electrons can be produced from electrodes of different metals. So they use one metal because metals are really good at conducting electricity. So they could, based on the photoelectric effect, you could put energy on a metal and then it would emit electrons or emit photons. Or you put photons onto it, it emits electrons. So that's photoelectric effect. They could use that concept to project the beam of electrons. So basically, J.J. Thomson, electron. Next, then he was like, all right, if this is the case, then what we can say is that there are these things called electrons, but the rest of it is kind of just like a sphere of positivity. That's what I want this classroom to be, a sphere of positivity. So, or this Zoom room, whatever. So this is one way of them representing the atom at first, his plum pudding model. So I've never had plum pudding, nor do I want to have it. It sounds disgusting. But this was his model, his plum pudding model. it basically stated that you have electrons floating around aimlessly in the middle. They're going really fast and in straight lines. And then there's some sphere that's positively charged. And then you put those together and they make a neutral atom. All right, it's fine, whatever. But they didn't know what this thing was. So a lot of other experiments had to be done to figure it out. The next one that was done was Robert Millikan. So Millikan's oil drop experiment. He actually still focused on the electron. He wanted to know more about it because at this point, it was the only particle they knew about. They knew about how fast it goes. They knew about its general charge, but he could figure out more. So what he did is, here's one of the things he figured out. He calculated the mass of an electron to be 9.11 times 10 to the negative 31 kilograms. And that's important, not for this class. That's important for physics. So like, you guys have to take physics E&M eventually, right? Like this, I think it's physics 2, maybe, I don't know. Yeah, so that class, you have to, that's one of the fundamental constants, the mass of an electron. So, is there a thing? They don't show it. Oh, they don't talk about his oil drop experiment. All right, fine. I guess we're not talking about it. Basically, he put some stuff in a chamber and it went towards. So it was actually really. I'm gonna talk about it. It's really cool. So he put charged particles. So the way you can charge particles is what we call ionization. So ion. We're gonna learn about ions today, which have either a positive or negative charge. You could induce a charge by kicking off electrons of any atom. This is called ionization. You can ionize basically everything or anything. So they put them in this chamber, these random particles. Then he ionized them with really strong radiation. Now, in his box, they put it in this box. The top of the box was positive. The bottom of the box was negative. These droplets of atoms were so light that the gravity, or that there was two forces on it. There was gravity pushing them to the ground, and then there was the positive, negative, attractive forces attracting them upward. And they would actually levitate. And also he can change the positive force to make it higher, or positive electric field to make it higher or lower in voltage. So at a certain point, they levitated. Where they levitated, or how much energy or how much voltage it took for them to levitate, from that data, he was able to calculate the charge of the electron and also the mass of the electron. Based on gravity, gravity's pushing it down and the charge is pulling it up. So from the data, a lot of calculations later, he figured out the mass and the charge of an electron. So that's pretty cool. We have a question. Oh, it's okay. All right.
Oh, thank you.
Yeah, no problem. All right, so radioactivity. So this guy, Henry Becksquirrel. No, that's not how you say it. I'm not going to pronounce it, whatever. So he discovered radioactivity by observing emission of radiation by uranium. So these are the three main types of radioactive particles that we're going to be exposed to in this class. And there's a whole chapter going over them. So this is kind of just an overview. So the first one are gamma rays. So gamma rays will kill you. They are the highest energy radiation. And there is the Greek letter gamma. So it looks like a cool fancy Y. And it's basically high energy photons. So going at very, very high energy, and they will go right through you, give you cancer really bad. Then there's beta particles. Beta particles are high-speed electrons. Not as much energy as gamma rays. So a lab coat will block them. This screen will block them. So yeah, they're not too bad. But they can penetrate skin. Then you have alpha particles, where a light piece of cloth could block them, or paper. And an alpha particle is basically a charged version of helium. So it's actually helium. They have an atomic mass of 4, they have 2 protons, and they have no electrons. So it's positively charged, high energy helium particles. That's what an alpha particle is. And because it's helium, because it's an atom, and the parts of helium are so much heavier than an electron and a gamma ray, which is a photon, which virtually has no mass. then it's going to be a lot slower and it's a lot less dangerous. So alpha particles aren't really dangerous to us. And it has a mass, and right there, of 7,300 times that of an electron, because it's got 2 protons and 2 neutrons. Okay, so any questions there? Any questions yet? So far, it's just information. I know it's kind of boring. All right, moving on. Rutherford's experiment. So he had this gold foil experiment, basically like aluminum foil, but more expensive. Now, in his gold foil experiment, he set out to prove something. And I'll just show you the figure. So here we have it should be lead. This is a brick of lead, right? And you have a source of alpha particles in a cylindrical piece of lead. The reason why we use lead is because lead deflects radiation very well, so it doesn't escape. So you have, let's say, 100 particles that are coming out of this source. 100 particles go through, and on the other side, you have a slit with a piece of gold foil in the middle. So this gold foil, based on Thomson's plum pudding model, is a bunch of some kind of invisible or visible, they didn't even know. It was either a solid or not solid, positive force sphere thing, and then a bunch of electrons that are really tiny. All really close together because it was a gold foil. So they didn't really know what was going to happen. They expected, and basically what happened, they shot the beam at the foil, and around here is a detector. It's like a 360-degree detector that can detect, let's say, out of 100 particles, how many are hitting at different deflection angles. So all the scientists out there were thinking, all right, one of two things is a perfect experiment, but one of two things is going to happen. It's going to go right through, which that means most of every atom is empty space, and it's just, then Thomson was right with his plum pudding model, and it was just some kind of invisible positive force with electrons in it. Sure. The second case is, what if that positive force was solid? They would all bounce off, and they would all bounce directly back. So those are the two options. But what actually happened is, as you can read, most particles passed through the foil. About 98% of them went right through. But that's not the most important part. The most important part is what didn't go through. So you have a very small level, about 2% of scattered particles, whether they be in all different angles. So this means that, wait a minute. And they did this multiple times, so that wasn't an error either. So they're like, all right, wait a minute. Based on those statistics, that might mean the atom is 98% empty space, and that 2% is something solid. So J.J. Thomson was like half right. So, or actually he wasn't right at all, but like if you average out both of his ideas, they'd be right, but whatever. So, okay, that's weird. Now they knew the electrons were fast. They knew the electrons were on the outside. So they were like, all right, then the little thing that is deflecting these alpha particles must be positively charged, because it's got to be that positive sphere thing. It's got to be that little 2% that's blocking the rays. So they're right, yeah. And they didn't know it had neutrons at the time, but by the mass, and by process of elimination of mass, they could figure that out, because the neutrons do have mass. So they know that, all right, there's a little dense particle. And then you get the idea of the nuclear atom. So, which basically is Rutherford's conclusion, that the nuclear atom has a dense center of positive charge called the nucleus, with the electrons moving around the nucleus at a relatively large, or that's a distance large, well, the distance varies basically. They're far away, but they have different energy levels that we'll learn about later in the course, that the electrons can move around at different speeds and different energies. So you have the electrons moving around, protons and neutrons are in the middle. But they didn't know about the neutrons yet. They just knew that, all right, there's something positive in the middle. And to give you an idea of how dense the nucleus was and how small it was. So picture Yankee Stadium, right? Huge stadium, fits 55,000 people. Empty it completely, but just have like the thousands of tons of steel and concrete. Take a penny, put it on the pitcher's mound of Yankee Stadium. Then put all the mass of Yankee Stadium, all the thousands of tons of concrete, into the penny. And then that's your atom. You have all of that mass inside the penny. Meanwhile, the rest of the Yankee Stadium is completely empty. That is the representation of atoms. That's how small the nucleus is compared to the rest of the atom. And that's 98% or so is empty space. So that means every object we're looking at right now is 98, and us included, 98% is empty space. So if you want to insult somebody, you can say, yo, you're 98% empty space. And you're right. So that's a fun fact. But the reason why we don't just fall through things is because we are also empty space, but that space is, from nucleus to nucleus, is angstroms, which is actually smaller than nanometers. It's between picometers and nanometers. It's angstroms. A couple of angstroms difference from nucleus to nucleus. If that, it's usually closer, usually picometers. So that distance, with billions of them per square centimeter, trillions or quintillions per square centimeter, virtually makes a solid object, even though 98% of it is empty space. So that's weird. But yeah, cool. All right, so here's just Rutherford stuff revisited. So here's what you'd expect with the plum pudding model. Is you'd expect, oh, it's just some random positive sphere that you could go through. All right, everything would go through. But that's what they actually observed. You have a positively charged nucleus. And most of them went through, but only 2% didn't. And that 2% is the most important part. So they had to do this a lot of times because those detectors were in the 1800s. So they weren't too precise or too sensitive. So you needed to make sure he wasn't seeing systematic error from last class. Okay, so here is a summary of all the dudes. You got Dalton, who's like, oh, there's atoms everywhere. Then you got J.J. Thomson, who's like, yeah, they have electrons, they have a charge, they have a mass. I figured that out. And plum pudding. And then Rutherford's like, no way. And he's like, gold foil experiment, electrons are there, but there's also the small dense nucleus, which is positively charged. So then all that information together, you get the modern day atom, the modern day atomic structure, which has the protons, the neutrons in the middle, and then the electrons on the outside. So any questions on that? Yes?
Would Rutherford's experiment happen if the other guy didn't do the plum?
The plum pudding dude, the J.J. Thomson?
Oh, wait, actually not him. The
Millikan?
one with the cathode?
Oh, J.J. Thomson, yeah, that was Thomson also.
Oh, yeah.
Yeah.
Would Rutherford have gotten that idea if J.J. Thomson?
You know what? Probably not. But there would have been some other scientists too. So maybe, I don't know. So that's how discoveries are made. There's got to be somebody to do it. But if he didn't do it, somebody else would have sooner rather than later, I guess. Because that's when this was groundbreaking science back in the day. So there was a lot of groups studying it in the 1800s. So they would have eventually figured it out, but he was the first one to do it. So it would have taken longer. Yeah, so that's a good question, because you have to make, so sometimes in new discoveries, the science is wrong. And it's the next generation's scientists to look at their data and build on what they already did and say, all right, this doesn't seem right. We could do this experiment A, B, and C to validate what the previous guy did or girl did. And that's exactly how discoveries are made. Because not every paper, so actually here's a fun fact, about 40% reputable scientific papers have false stuff or fake data in them. So that's weird. So imagine how my PhD is going, where every 40% of the papers I read aren't true or reproducible. It's a pain in the ass. But you actually learn to critique data. It's weird. Like normally, like when I first started PhD, I would take every paper I read as, okay, that's true. It's like written, it's in Nature. Come on, it's true. It's gotta be true. But then like now I look at the graphs better. I look at everything. I'm like, how did they get it to look that nice? It's probably like really exaggerated. And then like I look at the methods and I'm like, all right, I know that's not what they do for this. And like, because you end up getting to a high level. So you end up questioning the world around you, which is great. Okay, moving on. So the neutron, we talked about how small and dense the nucleus was. So this is important, but not really the mass in kilograms. So what we will be talking about in this class for the 3 subatomic particles is the mass in AMU, which is the atomic mass unit. And you can write this down in your notebook, but I'm sure it will show up, that the electron has a negligible mass in this class when we're talking about finding out the mass number of an isotope. When we talk about the average atomic mass, we're not really factoring in the electrons at all, because as you can tell by the kilogram mass measurements, proton and neutron are very close together, but the electron is 10 to the 4th less than that. So 10,000 times less than the proton and neutron in magnitude. So it's pretty much it's pretty much like negligible, right? So in terms of this AMU, you can write it like next to it. So proton and neutron have the same mass for our intensive purposes. They have 1 AMU. So the mass number, we'll learn about that in a second, but I'll just tell you right now, the mass number is the mass of a specific isotope that's calculated by adding the protons and the neutrons. So it's basically the mass number equals P plus N, protons plus neutrons. And the protons and neutrons are 1 and 1 AMU respectively. So you just add them up. And then the charges are important. So electrons are -1 charge, the protons are +1, and the neutrons are 0. So here's a fun fact. The neutron is actually heavier than the proton and the electron put together. You would think, even though I teach that they're the same mass, approximately, if you add the proton and the electron, it's less than the neutron. That's pretty cool. Okay, any questions on that? No? Okay. All right, isotopes. So we talked about that a little bit, but let's get into it with notes. So isotopes, basically, if you break down that word and make it Americanized, isotypes, types. They are types of elements. So, or types of atoms. So an atom with the same number of protons, but different number of neutrons. So same number of protons. The number of protons, otherwise known as the atomic number, is the most important number when determining what type of element an atom is. So what that means is the proton is the characteristic of the element. There is no such thing as oxygen that doesn't have 8 protons. Every single oxygen has 8 protons, every isotope. There's oxygen 15, oxygen 16, and oxygen 17, I think. Really just 15 and 16. Mostly 16, it's like 99% oxygen 16. But even for oxygen 15, it still has 8 protons. It just has 1 less neutron. So that's true for that. They depict almost identical chemical properties. I did mention that before, that when you react them, there's virtually no distinguishable difference in the way they react. That's why it's tough to discover them in the first place. In nature, most elements, whatever, they contain mixtures of isotopes. Yes, and they all do. So here's an example of 2 sodiums. Now here we have 2 symbols that are on the bottom. We have the Na, which is Na is sodium, with 23 on the top and 11 on the bottom, and the other one has 24 on the top and 11 on the bottom. So we'll learn about that in the next slide, but who can guess what the 23 and 24 is? Or who can not really guess? Who can tell me? What do they think it is? Yeah.
The number of neutrons?
Huh?
No.
Protons and
Yeah, protons and neutrons. Yeah. So it's the number of protons and neutrons, otherwise known as the mass number. So the top number in this symbol is the mass number. And it's specific for each isotope because the mass number changes. So if you add one more neutron, so this isotope of sodium has 12 neutrons, the one on the right has 13, the mass number changes by 1 as well because the protons are held constant. Because the protons are the characteristic thing of that element. They do not change. So the bottom number is the number of protons. That's what I was going to ask next, but I answered that for myself. So yeah, any questions on how those two isotopes work? Is there anything that's not clear about the isotopes? I'll answer that. No? Okay. See why every time I teach a class, my phone blows up. And normally nobody bothers me, but only when I'm teaching people bother me. Okay, so here's that symbol. So we're learning this symbol first. This symbol is not what you're going to see on the periodic table. They're different. We call this the nuclear symbol. That's not the correct atomic number for sodium. Who did that? I didn't write this. You can blame copyright 2018 Cengage Learning. It's their fault, not mine. Hear that, YouTube? It's their fault. So, before somebody in the comments, yo, this guy doesn't know chemistry, yo. Anyway, so this is the nuclear symbol. It's not on the periodic table. The periodic table has the periodic table symbols with the average atomic mass and the atomic number, which we'll talk about later. So your mass number is on the top, atomic number or proton number on the bottom, and your element name is the symbol.
so a nuclear symbol is specific to an isotope. Right?
Perfect, yes.
Okay. And then the other way around is
Yes, yes. So the nuclear symbol, these symbols are specific for each isotope, whereas the periodic table symbol is an accumulation of the average data of all of the naturally abundant isotopes of an element. So good job. Any questions on that? No? Okay. Cool. Critical thinking. Who cares? Right. Okay, this is good. Yeah, so write the symbol for an atom, or you can just tell me the symbol. For an atom that has an atomic number of 9 and a mass number of 19. So without looking at a periodic table, I'll tell you that 9 is fluorine. So F. So where would the numbers be? Someone could just tell me out loud, or anyone online. Like, what would the symbol look like?
19 over 9 with the F for fluorine.
Perfect. So yeah, 19 on the top is the mass number, 9 on the bottom, that's the proton number, and then the chemical symbol, which is fluorine. Perfect. All right, get it? Oh. Okay, so, well, I guess we could talk about this. There'll be more examples, because we didn't see the periodic table yet. So here's some examples, and with only the mass number shown. So it's asking for how many protons and neutrons are in the nuclei of each of the following. So for bromine, which is the first one, Br, what you have to do is you look at the periodic table. You see the number for bromine, and the number for bromine is 35. So you would know that 35 goes here, underneath the 79. Or so people can see online, 35 goes here. Then you know that the mass is 79, the protons are 35. It's also asking for how many neutrons and how many electrons are present if it is neutral. So for the neutrons, if you have 79 as the mass and 35 as the protons, how would you find the neutrons?
Subtract the atomic number from the mass.
Perfect. You subtract the atomic number from the mass. So it would be 79 minus 35 to get 44. And that would be the neutron. So we'll look at the first one there. And then for the number of electrons, it says in a neutral atom of each of the following. So if it's neutral, that means the protons and the electrons have to equal each other. That's what neutrality means. Proton pluses equal minuses. So you get that. Okay, so actually what I'm going to do is I'll take a 2-minute break and you can use your phones to look up periodic table. Do the rest of those. I feel like I'm boring you guys to death, so do something different. I'll give you until 59, or not, yes, 6:57, give you until 59. Okay, so for number 2, anybody can give me their answer for protons right off the bat. What do you think it is?
35.
35, good. It's bromine, every bromine has 35. What about neutrons?
46.
Good, 46 because it is 81 minus 35. How about electrons? 35 again, yeah, exactly. So next one, Pu. What is the protons?
94.
Good, 94. So yeah, you look at the periodic table and you see that you find Pu, it might take a while if you're not familiar with the table, and then you find Pu, which is 94. What about neutrons?
145.
Good, 145. So it's 39 or 239 minus 94, 145. And electrons would be the same as the protons, which is
94.
94. Good, awesome. Okay, and then the cesium, I'll give you guys a break. We have that, and it's the same kind of approach. So, good. Okay. There's another one. You don't have to do that. We'll do this. So, which of the following statements is true? So the number of protons is the same for all neutral atoms of an element. Yeah, I think that's true, right? Number of protons is the same for all neutral atoms of an element. Yeah. Next one. The number of electrons is the same for all neutral atoms of an element. Yeah, looks good to me also. Third one. Number of neutrons is the same for all neutral atoms of an element. No, because of isotopes, because the neutrons change. So then those two are the right answers. Okay. All right, any questions on isotopes before we continue? Okay. I feel like am I going too slow, too fast? Or? Good? All right, cool. I don't want to bore you. If anybody has any critical feedback, please give it to me. Whether it be on online quality of you can hear me or not, or lecture speed. So, chemical bonds. So now we're going to kind of switch gears a little bit. Now, chemical bonds are the forces that hold things together. There are 2 types. Two main types. There's covalent bonds and ionic bonds. We'll talk about covalent bonds first. So covalent bonds are formed between atoms that share what we call valence electrons, but we can just say they share electrons. So these valence electrons that they share, they're actually the outermost ring of electrons. And it makes sense that those are the ones that interact, because if you take 2 spheres and you collide them together slowly, what's the first part of each sphere that's going to hit each other? The outside. So the outside electrons are the first ones to react based on physics. So that's a covalent bond. It's formed by sharing electrons, and the sharing of electrons causes them to stick and causes them to bond. So yeah, we get it. Okay, there's different ways to model them too. So chemical formula is one way to model a covalent bond, or really any bond. And for example, CO2, you can tell that there's 1 carbon and 2 oxygens. We kind of talked about that already. Then there's 3 more, which are the structural formula, which is important. And once we talk a little bit more about organic chemistry later on, and we'll cover electron configuration, Lewis structures, things like that to write out the 3-dimensional formula. So here's an example of the structural formula. It tells you how the atoms bond. And something like this is methane. Well, they're all methane. So these are all methane, CH4. You can write it just as CH4, or you can write it like any one of these, which show the actual bonding patterns. This is important because CH4 is pretty easy. But when you get to more complicated things that have O, H, and amino acids and stuff and sugars, you need to know the connectivity, the way they connect. The formula isn't enough. So a picture like this is the most used in chemistry, especially organic chemistry. So anybody here need to take orgo eventually? Yeah, so you're gonna be seeing this a lot. Way more complicated though. Okay, then there is the second type of bond called the ionic bond. And they are ions, so ions. An atom or group of atoms with a net positive or negative charge. Multiple of these, multiple ions make an ionic bond. If you have a positive and a negative one, they make an ionic compound. So the difference, one of the big differences between ionic and covalent, besides the fact that they react differently, meaning covalents have sharing electrons, and ionic bonds use charges, is that ionic bonds don't have a symmetry, they don't have a geometry. So what we saw in methane is we saw different shapes. This is called a tetrahedral arrangement. When we deal with ionic bonds, there's no real shape going on. It's just one blob is sticking to one blob. It doesn't, and the orientation constantly changes because it's based on charge, not based on position and which electrons are being shared. It's just based on position. So the positive ions, so in an ionic pair, there's a positive and a negative. The positives are called cations. So the easy way I think of that is I have a cat and I like cats, so that's positive. So cation, positive. And what the cations do, in order to form their positivity, they are losing electrons. So they start out as neutral. When they lose their negative electrons, they become positive. Is your question? No? Okay. Anybody have a question online? I heard someone say something. No? Okay, I'm hearing things. Okay, the negative counterpart to a cation, which is positive, the negative one is a anion. So think of anti, against, whatever, anion. And that is a negative ion that they're formed by, instead of losing electrons, by gaining electrons. If something gains negatives, it becomes more negative. So that's that. And then when they go together, they make an ionic bond. And a prime example is sodium chloride. So the cation will form from Na, which is a solid, and it will be ionized. It will lose an electron, and then chlorine will gain the electron. So I think I have a GIF in a couple of slides showing the formation of ionic and covalent bonds. It's actually pretty cool. So ionic solids. So there's a lot of solids that are made of ionic bond. Every salt you can think of, not just NaCl, but Rhodes salt, but any kind of most crystal things, like any antacid is going to be like either magnesium carbonate or calcium carbonate. Those are ionic bonded things together, and they're in a solid form. So, and those things can contain polyatomic ions. So we'll learn about this actually today, more in detail later on. But a polyatomic ion is an ion that has either a positive or negative charge, usually negative, that contains many atoms. So it's kind of like, it's the same exact thing as Cl minus, but it's not just one atom like Cl minus, it's maybe 3 or 4. And then the whole thing, the whole group of 3 or 4 has a minus charge. So examples, you have ammonium nitrate. So that's NH4 plus, which is a polyatomic ion by itself. And you have nitrate, which is NO3 minus, which is an anion. And then when you add them together, the plus and the minus will cancel out, and you get a bond. Okay, so how is an ion formed? Either by adding or subtracting protons from the atom. True or false? Good, so A is false, of course. We cannot move the protons, because then you change the type of element. You can't do that. B, by either adding or subtracting electrons from your atom.
Yes.
True, yes, that is true. By either neutrons, no, and no. So it's B. An element's most stable ion forms an ionic compound with chlorine and has the formula XCl2. We didn't really learn this yet. Okay, but I'll just tell you. Why is this question not here already? All right. So chlorine. So when we did see it though. So chlorine, when it forms an anion, it gains 1 electron, and we'll learn more when we get to the periodic table of why it gains that electron. But when it does, it becomes -1 charge. So chlorine is always going to be -1 charge. If that's the case, if you have some random element X Cl2, that means what does the charge of that X have to be?
+2.
Good, +2, right? Because each Cl is -1. There's 2 of them, so -2. Then whatever is remaining to cancel it out has to be +2. So whatever this element that they're talking about has to be +2. Now, if the ion has 36 electrons, what is the element? So if it's 36 electrons, 36 minuses, and its total charge is +2, how many protons does it need to have? Good, 38. Good job. So 38. So 38 minus 36 is +2. So if you look in the periodic table, you will see that strontium, Sr, has that feature of having 38 protons. So that's what that would be. Also, if you knew, so strontium is on one of the trends that we're going to learn on the periodic table when it comes to charge. It's in the second group. So in the periodic table, there's groups. I don't know why I'm waving my hands around, but there's groups. There's group 1A, 2A, etc. Strontium is in 2A, and it has a charge of +2. That's something we're going to learn about those groups. Okay, and we're going to get into that now. So we'll do periodic table. Yeah, we'll do periodic table, and then we'll take a break for like 10 minutes. Okay. Periodic table symbol. So the symbol, there's carbon. It's different than the nuclear symbol, as I mentioned. And the key things to know is that the atomic number is now on the top. The atomic number is on the top. That means for every carbon, all of them have an atomic number of 6, meaning they have 6 protons. The atomic number is the number of protons. The bottom number, the middle is obviously the symbol. The bottom number is the atomic mass, otherwise known as the average atomic mass. So the average atomic mass is, like I mentioned, the weighted average of the isotopes that are abundant in nature of that element. And factoring in their natural abundance percentages. So even if you didn't know the information that I said before about the abundance of carbon 12, 13, and 14, just by looking at the average atomic mass, you can tell that most of the carbon atoms in existence are carbon 12. Because the weighted average, the 12.01, is very close to 12. So that means most of them have to be 12. And then the atomic number of protons, super important. And the mass is the protons plus the neutrons. That's what we talked about already. Okay, so any questions on that? Don't feel like you have a stupid question, you don't. Because if you have the question, I guarantee someone else does. So it's important to ask questions. I mean, if you seriously don't have anything, that's fine too, but. Okay. All right, periodic table, boom, there it is. Memorize it. No, I'm kidding, don't memorize it. So I want to see what you guys would look like. But I can't tell on facial expressions under the mask, so you're just like, oh, okay. But there it is. So it's color-coded, that's good. And we're gonna learn about each one of these. This is actually a good place to break. We'll learn about each one of these color codings once we take our break, after we take our break. So it's 7:12 now. All right, cool. So it's 10:20, not 10, it's 7:22. All right, continuing. Periodic table, here it is. So let's talk about it first, and then we'll learn different properties of it. Now, general things. All of the most of the elements in the periodic tables are metals. The metals are located on the middle, transition metals, and also on the left over here, not hydrogen. On the bottom here are metals, and also over here are metals. These are metalloids, and then there's non-metals to the right. So there's only 17 nonmetals. There's 80 something metals, and there's like 7 or 8 metalloids. So those are the main 3 types of elements: the metals, the nonmetals, and the metalloids. And it makes sense how the metalloids are somewhere in between physically of the metals and nonmetals, and their properties are the same thing. They're in between. So silicon semiconductors, right? So every computer we know is silicon, also germanium. So those are key semiconductor types of metalloids, and they have key features which we'll talk about soon. But here we go. Now, color-coded, we have, I keep pointing. All right, so color-coded here, we have the group 1A, which is important. We have 2A, and then, so you notice these group numbers. There's 1A, 2A. We skip the entire middle section. This transition metal section, we skip it when we're naming these groups. And we go to 3A all the way through 8A. The reason why we do that is because the top ones, or really not the transition ones, are called the main group elements, and they have specific features when it comes to valence electrons and when it comes to their charge. That's going to be very important to know and to memorize the different group charges when it comes time for naming and when it comes time for forming ionic compounds. And the main group ones do not have a variation in charges, meaning the middle ones, they do. So transition metals, the word transition means it's changing from one thing to another. So these transition metals, I mentioned iron before. So iron has multiple states. It could either be +2 or +3, which means you could have 2 valence electrons and lose them, or 3 valence electrons and lose them. So it could transition. Some of these things have more than 2. Like some of them have 1. Zinc so zinc is right here, and silver, they only have 1 state. So zinc is every single time +2, and silver is every single time +1. But the other ones in here all change a lot. And even the ones over here change a lot. Lead could be 1, 2, 3, or 4. Tin could be even 5. So aluminum is only 3. So the periodic table, the more we learn about it, the more you're going to hate it, because there's exceptions to it. And it's like, oh, this makes sense, this makes sense, oh, that doesn't, this makes sense, that doesn't. And it's like, there's a lot of different exceptions to it. And the best way I can describe these exceptions are, this is the best way that humankind has figured out to organize every element in the universe that we know of by chemical property. So they go in order of the number of protons. They set it up in such a way that that order, 1, 2, 3, 4, 5, 6, boom, boom, all the way down to 118, that order makes columns that have similar chemical properties. Those columns have the same number of valence electrons for the most part. They have the same charge for the most part. They're the same type: alkali metals, alkali earth metals, transition metals, halogens, noble gases for the most part. This is random hydrogens here, like a non-metal just sitting there, but hydrogen's weird. So it's the best representation of what we have. Weird things, what's on the bottom? Lanthanides and actinides, where do they belong? They belong right here. Why aren't they there? You know why? Because the page isn't big enough. That's actually why they put them on the bottom, because the page isn't big enough. And also it would mess up the group numbers. So we don't consider them to be part of any group. So other things is you have the transition metals, and then you have this weird section. No point in going over there. This weird section. So not the metalloids, but underneath on the left side of the metalloids, gallium, indium, tin, I think it's thallium, lead, bismuth. They are also these other ones, which are whatever. Those are what we call post-transition metals. Literally transition metals, but they didn't know where else to put them. And it wouldn't fit, if they put them somewhere else, it would mess up every other trend they got going. So they had to just find the best solution. So it's not perfect, it's got exceptions, but it's the best that we can do to represent everything we know. and make it easy for Chem 1 students to understand and easy for everyone to look at to find what they're looking for. All right. So general properties of metals. No, I'm not really going to dwell on this too much, but metals, they're really conductive. They conduct electricity. They conduct heat really well. They're malleable. They look like metal. They're like lustrous. And most importantly, when they form ionic bonds, they lose electrons. They're going to lose the electrons. And we'll talk about why soon. Non-metals. Non-metals, they have they're like brittle. They're really brittle. They're either solid, liquid, or gas. Metals are all solid. They're brittle. They don't really conduct electricity at all. Kind of boring. We need them to live. That's good too. Oxygen's important. All right. Also, the most important thing is they tend to gain electrons when they react with metals and they form their negative anions. That's important. All right. So going into the first group, Group 1A. So elements in vertical columns have the similar properties. Those are called the groups. The first group is 1A, which is the alkali metals. They all have +1. They're very reactive with water. They explode if you put water on them. So something I'll do, I have actually a little vial in my desk somewhere of sodium metal. So I should bring that in one day. I told my class here last semester that I'll do that, but I never did it. I don't know why, but I could bring it here and like pour water on it and do what's that'd be pretty cool. I could do that. If someone walks in, I'll probably get in trouble, but I don't care. Whatever. I'm a rebel. They can't afford to fire me. Who else can teach the class? Like, there's like a hiring freeze everywhere. So anyway, so yeah, they are very reactive, and they tend to lose 1 electron. So I guess I'll cut to the chase when it comes to this charge thing. They end up having a +1 charge, and the reason why is because they want to lose 1 electron. Okay, the reason why they want to lose 1 electron is so they can obtain the noble gas configuration for their electrons. Meaning, once we talk about noble gases on the other end of the periodic table, they are happy. Their configuration of electrons is the most stable configuration of electrons there is, the noble gases. So every other atom in the periodic table wants to either gain or lose electrons to get to that noble gas status. So that's why we even make ions in the first place. That's why they're energetically favorable, because it gets them into this noble gas-like configuration. And what that means is their P shell is filled up, if you want to get into configuration. But that's for another chapter. Then you have group 2A, called the alkaline earth metals. So it's very similar to alkali, but it's like alkaline, like batteries, right? Alkaline batteries. So alkaline earth metals, they have +2 charge. So they tend to lose 2 electrons when they form ionic bonds. So they're +2. Okay, that's about it. They're reactive, but not as reactive as the first group. Then we are going to go to the other side of the table, to 8A and 7A. So there's really only 4 important columns. There's the group 1A +1, the group 2A +2, and then you go all the way to the other side. There's the noble gases, which are 8A, and there's the halogens, which are 7A. So we'll talk about the halogens first. The halogens, most of them are diatomic. I think all of them are. Yeah, all of them are diatomic, meaning that when they form in their natural state at room temperature, they are with a 2 on them. So F2, Cl2, Br2, I2. So they form in a diatomic gas state. So fluorine gas is F2, chlorine gas is Cl2, bromine gas is Br2, etc. And they gain electrons, except for astenine, which is on the bottom, it's weird. They gain 1 electron to get to their goal of a noble gas configuration. So once they gain that electron, they become positive or minus -1 charge. So let's look at fluorine. Neutrally, so the protons are 9, the electrons are 9. If it gains 1 electron, it gets to 10 electrons. That's the same thing that neon has. Neon's happy. Neon's a noble gas, so we're good. If we have sodium, if you picture the periodic table, it's where my cursor is. It's on the next level. Once sodium loses 1 electron, it ends up with the same configuration as neon. Therefore, it's happy. So when sodium reacts with fluorine, both of them have the same exact electron configuration because fluorine gains the electron to get there, and sodium loses the electron to get there. And sodium gives the electron to fluorine. And that one motion of giving the electron to fluorine makes them bond together. Like, oh, you gave me a gift, let's be friends. Boom, and they make a chemical bond. And they're both happy. Okay, next, noble gases. Group 8A, they're here and they're happy. They exist under normal conditions as monatomic. They don't like to react with anything. They are called inert. So they have very little activity. Yeah. Okay, so that is the goal of every one of these atoms, is they want to get to a noble gas configuration when they bond with something. That's a key concept. Okay, any questions on that? On different groups? No? Okay. Horizontal rows. So the horizontal rows are called periods. Honestly, there's not much important about periods because they don't have much in common with each other. The only thing that periods have in common is that they increase by 1 as you go through it by proton. So francium has 1 less proton than radon. Radium, that's radium. So yeah, that's really, there's nothing in common with them chemically. As you can see, you have metals, you have metals, non-metals, and weird stuff, and then you have noble gases. So there's nothing really in common with them. And then you have valence electrons. So we dabbled with this idea of these atoms want to become happy. And I know that we're bouncing around a lot of ideas, but it's just, we'll delve into each one of these. Maybe not all today, but some of them. So the valence electrons are the electrons on the outer shell. They react with valence electrons of another element, or another atom that's nearby. And the goal for these valence electrons of any atom is to get to 8. Why 8? So 8 is the number that fills up the 2 main orbitals, the s orbital and the p orbital, which we didn't learn about that, but there's two electrons in the s orbital, 6 electrons in the p orbital, 2 plus 6 is 8. And that's your happy state. 8 is your happy state. I made that up. So the metals like to lose the electrons to get to that point. So their electron configuration goes from, let's say, where sodium, if you picture a periodic table here, sodium's here, it would go back all the way up to the neon configuration. And then the nonmetals, they're going to gain the electrons. So the nonmetals gain, metals lose. Yeah. So any questions on that? Any questions at all from anybody online or here? No? Okay. All right, so here is a GIF. So this is important. This is sodium fluoride. Now, sodium will lose its electron. It will give it to fluorine. That will induce their charge. And then they will come together based on the new charges. So I've heard it taught wrong before. I've heard that once the atoms come together and bond, the electrons will transfer. It's the opposite. The electrons will transfer first. The electron transfer induces the charges on each of the elements, on each of the atoms. That induced charge brings them together. The reason why they randomly just, oh, sodium just, oh, here's, I'll take my electron. The reason why that randomly happens is because of this concept, or it's because of energy, really. So fluorine is super reactive and really has a really high electron affinity, meaning it really likes electrons. So any free electron or any atom that comes by that has an electron that is readily available to lose, it's going to take it away. So sodium, on the other hand, is the opposite. It has a very low electron affinity. So that means it's very easily able to lose an electron. You put both of them together, they're going to form an ionic bond really quickly because you have the perfect situation. So fluorine would be like, oh, can I have your electron, sodium? Yeah, take it, whatever. And then as soon as that happens, it induces a negative charge here because it gains an electron from neutral state. Positive charge here because it loses an electron from neutral state. And they come together. So that's how an ionic bond works. It's important to represent it as a GIF. And then covalent bond on the right side, it is the sharing of electrons. So it's the most simple covalent bond between hydrogen and hydrogen to make hydrogen gas. Each hydrogen by itself is neutrally charged with 1 electron each. Once they come close together, the electrons will start to share. So the electrons, as you can see, they start spinning around both nuclei. That's what we mean by sharing. And that bond is pretty damn strong. So there's always this debate, and it's taught differently in every school. What's stronger, ionic bond or covalent bond? I'm not going to give you the answer yet, but anybody want to give me any ideas? It's a complicated answer. Anybody heard something, or maybe from high school or something? I don't know. What's stronger, ionic or covalent?
Ionic.
Okay, that's an answer. It's a complicated answer. So whatever you say, you're going to be right, because the correct answer is it depends. Generally, covalent bonds are stronger, especially when you get into multi-covalent bonds, meaning the double bond and the triple bond. The double bond and triple bond are stronger than any ionic bond. But if you're just comparing single bonds, it depends. Something like hydrogen and hydrogen versus sodium and fluorine, I think hydrogen and hydrogen would be stronger. If you have a 2+ like magnesium and a 2- like oxygen, I think magnesium and oxygen will be stronger because a +2 and a -2 have a stronger plus and minus attraction force than a +1 and a -1. But it also depends on other things, which we'll learn about in a later chapter, like the atomic radius of how big each atom is. If you have the favorable thing is if you have 2 really small atoms that are heavily charged, really tiny +3 and really tiny -3, that's a crazy strong ionic bond. But it still won't be stronger than a triple bond of a covalent bond. So a covalent bond is king, but some ionic bonds are stronger than some weaker covalent bonds. So that's the answer that I found. Okay, so this chart is really important. I pulled this off of Google. And it shows the important charges that if you knew these for your exam or for homeworks, you'd be rock solid. So for charges, you have group 1A, we know is +1. Group 2A is +2. Group 3A is weird. Boron is covered because boron's a noble gas. Is a metalloid. It's been a long week and it's only Tuesday. Then you have aluminum and gallium are the only ones in 3A that all the time have a +3 charge. The other ones below it are those post-transition crap that it depends. So aluminum and gallium for +3. Then you have, it just so happens it works in a trend where it goes +1, +2, +3. But these are the ones, zinc, cadmium, and silver, that are in the transition metals, but are technically not transition metals because they just have nowhere else to put them. So you can, if you memorize that it goes, oh, +1 for silver, +2 for zinc and cadmium, +3 for aluminum, gallium, you could do that. So I would, but these 3 are, they're still important. It's a good trick question to give on a test of like, oh, name ZnCl2. And if you follow the rules that we're going to learn pretty soon, you'll think, oh, it's zinc 2 chloride. No, it's actually just zinc chloride. because it only takes one state of +2. So something to memorize, something to study. Then if you go to the right, start noble gases are always 0. The halogens are -1. The -2s, I don't even know their name. We don't even know. They don't even know what their name is. The oxygen, sulfur, selenium sometimes. Really oxygen and sulfur are the main two that have -2. Nitrogen and phosphorus are the main two that have -3. And you could ask, oh, what happened to carbon? Why doesn't carbon have -4? It could. It's a carbide ion. That's possible, but it's not really likely. I've seen it, but I guess in Chem 1 you don't really see it. Yeah. Okay, any questions on this, on the charge table? No? Okay. All right, so blank forms ions with +2 charge when they react with nonmetals. Which ones have +2? A, B, C, D, or E?
E, alkaline.
Yes. B, alkaline earth metals. I thought you said E for a second, but then, yeah, you said alkaline. So yeah, B, alkaline earth metals. Good. Because they're group 2A. Okay, so now we're going to try to name compounds. So we're going to name 3 types of compounds. Ionic compounds, which are probably the hardest of the 3. Covalent, which are the easiest of the 3. And then there's acids. Acids are in the middle. They're kind of like, it's just memorizing rules. It sucks. Just memorizing rules and practicing. So that's what we're going to do. We're going to memorize the rules, and we're going to practice. The first type is binary ionic bonds. So they contain a cation, and they contain an anion. And it's usually the cation followed by the anion. But there's a little bit of a change. So let's just talk about an example real quick. Sodium chloride. We know it's NaCl. Let's break it down. Na. Na is sodium. Sodium chloride. You write the name of the first one. That seems right. Boom, that's exactly it. The cation is always named first, and the anion is always named second. So whatever the metal is for the cation, you name it first. Sodium chloride, sodium. Second is the chlorine. So the element is called chlorine, but what I just said is sodium chloride. So that means there's some difference there, right? That's exactly it. You take the ending of the chlorine, INE, and you change the last syllable to IDE and make it chloride. Chloride, fluoride, oxide. It's not oxide. Nitride. It's not phosphoride, it's phosphide. Sulfide. Carbide. Yeah. So those are just some examples. And that's the second element, always the non-metal. The non-metal, you're making that non-metal name with an IDE ending. And that's how you name a simple ionic compound. So here's some examples. So as a cation, they would just be the name of the metal. So lithium, sodium, potassium, whatever, etc. But as an anion, that's when you change the name. Hydrogen becomes hydride. You're not really going to see the hydride much. Fluorine, you're going to see all the time. Fluoride, chlorine, bromine, iodine, oxygen, sulfur, nitrogen, and phosphorus. You'll see those all the time. So it's important that you're familiar with those endings. So iodide, that's one too. And oxide, sulfide, nitride, phosphide, bromide, yeah. Okay, so does that make sense? And then all you do is put those names together. So could someone tell me what would MgBr2, what would that be? Yeah, magnesium bromide. Another trick question, because I wanted someone to say magnesium dibromide, because I said MgBr2. There's a reason why we don't do prefixes for ionic compounds. I didn't mention anything about dioxide or disulfide or any of that stuff. We don't do that here because mathematically ionic compounds work out very well. So there only is one magnesium bromide. You can't have one version of magnesium bromide that's MgBr3. So magnesium is +2. Bromide is -1. So it would make sense that you need 2 bromides, -1, -2, to cancel out with 1 magnesium. And that is how every single ionic bond works. The pluses cancel out the minuses. Therefore, there can only be one name for every ionic combination. So cesium bromide. Cesium is +1, bromide is -1. Therefore, the equation is CsBr. Na sodium phosphide. Sodium is Na+, phosphide is P3-. What's the sodium? What's the formula for sodium bromide? Anyone want to tell me?
3Na.
Good, yeah. So instead of 3Na, it would be Na3P. Because you need to have 3 of the Na. So it would be +1, +2, +3, and then the P for phosphorus -3. Okay, good. Any questions on that? We'll do a lot of examples. So the rules. Fairly odd parents. Here's a slide that I made a couple years back, and this is only half the slide. It's a very comprehensive slide. And it's everything we just talked about and more. We didn't cover transition metals yet. We didn't cover polyatomic ions. But this is all of the rules of naming ionic bonds in a nutshell, in very concise notes. So you can take a look at this when you have time, but this is really like a summary of naming them. And you want to do, I'll put like just non-graded worksheets online. I think I have a couple of those just to on Canvas for just naming practice, because it's really important. Okay, so name each of them. I'll give you a minute to do that. Okay, so the first one. Anyone have a name for it?
Cesium fluoride.
Perfect, cesium fluoride. What about the second one?
Aluminum chloride.
Aluminum chloride?
Yeah.
Yep, aluminum chloride. Good. What about the third one? Might be tough. There's the hydrogen as the anion. So what do we call that? Call that hydride. Someone else? Did someone get it in the chat? Yes. Good job. Good job, Angela. So lithium hydride. Awesome. Cool. Super smart. Boom, boom. We're super smart. Yeah, got it. All right. Next. This is Roman numerals, right? Yeah. Okay. Cool. So the next is, you noticed that all the elements we just dealt with, we knew their charge. We knew their charge from that version of the periodic table with the charges listed. What if it's one of those elements that is blurred out in that chart? The ones in the middle, the transition metals. Basically, the name scheme applies still, but we modify it a little bit. So we modify it by using Roman numerals. Now, the Roman numeral, this second bullet point's important. The Roman numeral is the charge of each metal cation. And the Roman numeral is either for +1, it's 1, for +2, it's 2, for +3, it's 3. It's the charge of each metal cation, not the metals total of each one. So that's important. For example, if I had FeO, right? Fe is iron, O is oxygen. It would be iron 2 oxide, because oxygen is -2. So that therefore, phosphorus. Iron would have to be +2. So the +2 and the -2 of oxygen will cancel out. You get iron 2 oxide. That's a definitive thing. We're going to do examples on the next slide. But so keep in mind, that's only for elements that we don't know their charge from looking at the periodic table. So that's why it's very important to know the charges on the periodic table, because if you don't, you won't know which ones that you know and which ones you're supposed to know and which ones you're not supposed to know. It's important that you memorize them. All right, examples. Cu, Cl. We'll do this one together. So Cl, what's the charge of Cl? When it's an ion?
-1.
-1. Good, good. Yeah, and if you don't memorize it off the top of your head, like you just learned it a minute ago, it's okay. As long as one person maybe has their notes out or a periodic table. So yeah, chlorine's -1. It's in the halogens. What is the charge? What is therefore the charge of Cu?
+1.
+1. Perfect. So Cu is +1 because Cl is -1. +1 and -1 cancel out. Copper 1 chloride. So you have copper 1 chloride. Any questions on that one?
That's when you're writing it out with like letters like that. One.
Yes. So the way you're writing it out is very similar to number 2 over here, where instead of magnesium, this is 4 oxide.
Yeah.
You'd write copper, parenthesis, 1 Roman numeral, so an I, chloride.
All right.
Good question. Okay, so B and C. So who wants to do B? Hg is mercury. Any guesses? You know? Oh, sorry, I saw a hand.
Mercury +2
Mercury would be +2, yes.
and oxygen -2.
Mhm.
So it'd be mercury 2 oxide.
Perfect. So mercury 2 oxide. Oh, somebody answered it in chat. I didn't see. Good, awesome. Good job, Logan. All right, so mercury 2 oxide. Good, the oxygen is -2. Because oxygen is -2, mercury is +2. Now the next one's a little bit more difficult. So anybody want to tackle that one for me? We have Fe2O3. Fe2O3.
Iron 3 oxide.
Perfect, good. Iron 3 oxide. So here's what I'm going to use my pen for a second. It canceled the screen sharing, but I'll just add it again. All right. Okay, so for something like iron 3 oxide, it's a very easy way to do it. So if you have Fe2O3, watch this. It's called the crisscross rule. You do that, and you do that, and those are the charges. So of course, negative and positive when they apply, but good. Good job, Angela. So Fe would be +3. Now also, if you understand the concept of a common denominator, or what is it, least common factor, yeah, that's the same concept. So oxygen will therefore be -2. We know oxygen is -2. So if you have 3 of them times 3, that's -6. Therefore, Fe, if there's 2 Fe's, each one of them has to be +3. And that would be +6. So that cancels out, and you get Fe2O3, or iron 3 oxide, because remember the Roman numeral is the charge of the cation. It's the charge, not the number of them. So it would be iron 3 oxide, like that. Okay, so does that make sense? All right, so next one, so magnesium, or sorry, not magnesium, manganese 4 oxide. Beautiful, I like it. So manganese 4 oxide, so since we got the answer already, here's how I would do it. Or so here's a great example, because that rule I just said before with this crisscross crap, I don't like teaching this rule, even though a lot of teachers do, a lot of students like to learn it because it's easy, but it's not right 100% of the time. The math that I just said with the least common multiple is right 100% of the time. Doing it this way, and this is a great example, is not right 100% of the time. If you do the crisscross rule, oh, you put that in the corner, put this in the corner. You would get Mn, manganese, 2 manganese, and 4 oxygens. This is not the right answer. Why? Because it has to be reduced. So this can easily be reduced to, where to write it? I'll write up here. MnO2. And this is manganese 4 oxide, because this manganese, the oxygen is -2. There's 2 of them. Therefore, the manganese has to be +4. Any questions? Oh, okay. You beat me to the chase. All right. Isaiah and Angela, great job. You can teach the class for me for the rest of the year. I won't pay you though. Okay, so lead 2 chloride. So you guys already answered it. So lead is Pb2+. In this case, it's lead 2, and chloride is Cl-. Therefore, in this case, we can't do that crisscross thing. We can do put the 2 over there, put the 1 over here, or you can just think about it a little bit longer, like I do, and think of the least common multiple. So if you have 2 Cls, that would make them -1, -2. Cancel out with the Pb2+, and you have, I'll write it over here, PbCl2, like that. So Logan, good question. So the answer would not be Mn2O4, because that in the chemical nature is not how the compound behaves. If you look at each molecule of MnO2, there's not going to be randomly 2 of them next to each other. That's one compound. There's multiple molecules of MnO2. So it's important to simplify the ionic compound when you can. And most of them you're not going to be able to simplify, only if you have two even numbers. So it's rare, but this is a good example of how that crisscross thing doesn't work all the time. Okay, any questions on that? No? Okay. All right, so there's the answers. Nice, nice. All right, so we talked, this is just a flow chart going over different types, the basic ones or the transition metal ones. All right, so we'll do more examples because examples are good. So this one, CO is cobalt. So what would this be named as? Anybody could answer. Good. Oh, well, do we know the charge of cobalt? Or you don't? I'll just tell you, you don't know the charge.
I can assume it though.
Yeah, yes. What would it be?
I don't know. What's bromine?
Bromine is a halogen. It's -1.
-1. Then it'd be +1. That would be +2.
Good. Yes. So it would be cobalt 2 bromide. Good deduction right there. So we just learned about where the charges are and all that stuff. So it'll come to you when you do the homework. It'll make more sense. And then good, the next one, that would be, someone said the answer, calcium chloride, and not calcium 2 chloride, because calcium is in group 2A. So it's one of the ones that we're supposed to have memorized, the alkaline earth metals. Okay, next, chromium 3 chloride. Nice, you guys have beat me to the chase. So chromium 3 chloride. So the ions are Cr3+, and chloride we know is Cl-. So this one, you would need 3 chlorine ions to cancel out with 1 chromium ion, and you get CrCl3. Next one, I'm sure someone, I'm not going to look at the chat, somebody already answered it probably. So you have gallium, which is Ga3+, it's underneath aluminum. And then you have iodine. That's not an I. Sure. And iodine is -1. So then if you put those together, you would need the same kind of concept as the first one. You would need 3 iodines to cancel out with 1 gallium. So you get gallium iodide, like that. Great job, good. Okay. Seems like you guys are pretty quick on that, but anyone else have any questions? Because it may come fast to some people and not that fast to others.
Wait, if gallium has a charge plus 3, where do you have ring gallium together?
Oh, because we know gallium's charge.
Okay.
Yeah, so gallium is underneath aluminum,
Okay.
and that's one of the ones we assume. Okay, good. Good question. All right, so moving on. So here's another chart. This one's good too. I'll blow it up. Yeah, so I gotta share the screen differently. Yeah, so this is the same kind of chart I showed before, but it's more comprehensive in that it shows the ones that have multiple charges that are only 2, because the other ones, it's either, for a lot of the transition metals, it's either 2, some of them have 3, but most of them are like 4 or 5. It's either +1 to +5. And you don't know until what compound it's in. But for chromium, manganese, cobalt, iron, copper, mercury, lead, and tin, they have definitively 2 charges. And you don't have to memorize those charges, you don't. But just for your knowledge, that like, if you know this, and let's say you do an equation, do something on a test, and you end up getting like iron 4, you know that's not right because you took this extra steps to know a little bit more. So knowing your way around the PR table is good. Okay, so polyatomic anions. This is the part that sucks because there are about 15 or so popular or common polyatomic ions. Don't worry about the word oxyanion. We'll just cut to the chase of polyatomic ions. So here is a list of the common ones. Do you have to memorize all of them? No, but it would be good. You have to memorize some of them, definitely. So out of this list, I will say this. You have to memorize, don't really worry about the mercury, don't worry about mercury. You'd have to memorize all of them except for thiocyanate and oxalate and thiosulfate. And really peroxide, we don't really see peroxide too much. And peroxide. So you could omit from this list and you're maybe write it down or whatever, or cross it out. Thiocyanate, peroxide, oxalate, and thiosulfate. Those are the ones that we don't really see too much. And this is kind of like I'm giving you like a cheat because like I'm supposed to tell you to memorize all of them, but I'm telling you right now, you're not going to see those really on tests. And if you do, I'm sorry, and I'll give you extra credit, but you're not going to see them. So everything else, there's patterns in it, and it's tough just looking at it. Oh my God, I got to memorize all that stuff. But it gets easier as you experience them in different questions. So, and when you keep naming and naming over again, you'll figure it out. So we can go through a couple of them. So we can look at, so ammonium is the only one, we'll ignore mercury. Ammonium is the only one of a polyatomic, even though mercury is Hg2, it's not different atoms, different elements, whatever. So ammonium is the only one that's positively charged because it's just NH4 positive. We'll ignore that. Okay. Okay. So ammonium is the only one that's positively charged. It's positively charged 1. So then you have nitrogen containing ones, nitrogen and oxygen containing. There's 2. There's nitrate and there's nitrite. Very similar, but this is a pattern. Usually the ones with more oxygens are ATE, or 8. Sulfate, phosphate, carbonate. The ones with less oxygens are ite. So you have nitrate, 3 oxygens. Nitrite, 2 oxygens. Sulfate, 4 oxygens. Sulfite, 3 oxygens. Where's phosphide and Here's here, and here's the chlorates. We'll talk about that in a second. But okay, those are just two there. And then we have hydrogen sulfate, which is also known as bisulfate. Basically, take a sulfate, add a hydrogen to it, and it decreases the charge by 1. Hydroxide is a very important one. We're talking about acids and bases. Cyanide is Cn minus. It's different than the other ones. Kind of easy to remember. Phi is phosphate. Here's hydrogen phosphate, dihydrogen. Don't really worry about dihydrogen phosphate. But that's an easy one to know. It's an easy one to know. So you just add a hydrogen to it. And then if you add another hydrogen, it becomes phosphoric acid. And we'll learn about why that happens in a minute. And then on the other side, your carbonate is important, hydrogen carbonate. And then you have the 4 chlorates. So this works in a sequential way with the naming as well. So as we said before, the ATE endings always are the top level in terms of oxygens. And that's still true. Perchlorate. So perchlorate is like, oh, you're chlorate, I'm perchlorate. That's like above chlorate. So perchlorate is ClO4 minus. And the sucky thing is, they're all -1. It's just the way they work out chemically. So it's tough to memorize them based on charge because they're all the same. Then you go from, oh, I'm perchlorate, then the under level of that is just regular chlorate. That's where you have the ClO3. And then what comes after chlorate is chlorite. So you know the ite ones have usually less oxygens than the ate ones. So it is chlorite. And then to even get less than that, oh, you're chlorite, I am hypochlorite. Hypochlorite is the least amount of oxygens. And you're going to get ClO minus. So that's the story of the chlorates and chlorites. Permanganate, so these are the ones that are kind of like obscure. Acetate, you see it a lot. It's actually seen a lot. And it's C2H3O2. The way I remember it is CHO232. CHO232. CHO. And then permanganate is tough. MnO4 minus, just want to memorize. Dichromate and chromate are weird because you don't just increase chromium by 1 to go from chromate to dichromate. You have to make it Cr2O7. So, and each of them have the same charge. Those are kind of tough to know. But I would say if you're really familiar with everything on the left-hand column, and then up to all this acetate, up to acetate, you'll be really solid. So if you're memorizing, you're studying, just up to there is really good. And then to be perfect at it, everything, these 3 as well. So that's what I would expect. Okay, any questions on that? All right, and just to, I don't think I said this yet, but when you name with them, you're just naming the name. You don't change it to IDE ending, you just name it. So we can get on some examples right now. So we have Na2SO4. And I'll tell you, SO4 is sulfate. So what would the answer be?
Sodium sulfate.
Perfect. Sodium sulfate. Sodium sulfate. Then the next one. So the OH is hydroxide. What would it, and Mn is manganese. So what would it be? Oh, somebody answered it on the chat. Ooh, close. Angela, you're missing something. So she said manganese hydroxide, and I said it was wrong. Not to put you on the spot. So what's missing? Do we know the charge of manganese? Like from the periodic table? From the, is it in group, it's not in group 1A or 2A. Do we not know the charge of it?
It's manganese 2 hydroxide, right?
Yes.
All right.
Correct. Perfect. Oh, you corrected yourself. Sorry. Yes. Okay. Good job. So manganese 2 chloride, or sorry, hydroxide.
It's easy because of hydroxide. So like since hydroxide is 2, it probably should be 2.
Oh, I didn't tell you. Yeah, I didn't tell you hydroxide's -1. Whoops. That's why you're waiting for me to say that. So yeah, hydroxide's -1. So you have 2 of them. So then -2. So that means manganese must be 2. So manganese 2. Hydroxide. Cool. So I think, what do you guys think? If you had a week or 2 to study this, look it over, do the homework, you'll be fine. You think? Maybe, yeah. So it's just practice makes perfect with this. Good, manganese 2 hydroxide. All right, so now we're almost done. The only 2 things we have outstanding are are covalent bonds and acids. So covalent bonds, super, super easy. So, I'll stand up again. So, covalent bonds. They're formed, so we noticed in ionic bonds that it was always between a metal that was losing electrons and a non-metal that was gaining those electrons. In covalent bonds, it's different. It's between 2 non-metals. So only non-metals are partaking in covalent bonds. Why is a good question. It's because the non-metals, what do they want to do? They want to always gain electrons. So if you have 2 oxygens that come next to each other, one of them will be like, yo, I want to gain electrons. Give me some. He's like, no way. I want to gain electrons too. And they're like, what do we do? We don't have enough electrons to go around. What if we share our electrons? And then we can have our valence shells will be filled up with 8. Like, yo, dude, that's a crazy idea. Let's do it. And they end up sharing electrons. So they both want electrons, but they can't transfer one to the other because it would make the other one really unstable and not happy. So you have to share. So the naming. The first element in the formula is named first, using the first element name. Carbon dioxide, carbon. The second element is named as if it were an anion with the IDE ending. So carbon oxide. But then, prefixes are used to denote the number of atoms present, except for this rule. The prefix mono is never used for the first element. There's no such thing as monocarbon dioxide. It's just carbon dioxide. Why do they do that? Maybe because it sounds better. Mononitrogen sounds weird. I don't know. But I really don't know why they do that. That's the rule. So you can use, so the prefix, basically the prefix for the first element. You have to have a prefix for both, or you have to have the prefix to the first element unless there's only one of them. If there's only one of the first element, no prefix needed. Everything above 1, prefix needed. So let's just jump into prefixes. So what do I mean by these prefixes? So we know simple examples like carbon dioxide, CO2, dioxide 2. There are other ones. Mono is 1, di is 2, tri is 3, tetra is 4, like Tetris. Penta, and after tetra, it gets easy, it's just the shapes. So like pentagon, hexagon, heptagon, octagon, nonagon, decagon. So I would say the only ones, I mean, you need to know all of these, but the only ones that you may trip up on is mono, di, and tri. Usually di, usually for 2, it's like bi, a bicycle, stuff like that. There's no such thing as a bicycle. That's a cool name. But there is tricycle. There's no tetracycle. That's a car, I guess. So yeah, so those are, and then after 4, it just becomes the shapes. So yeah, example time. So let's name these 5 of them, or find the compound. So PCl5. Anybody want to give it a shot? PCl5. I'll give you a hint. Phosphorus comes first.
Just phosphorus pentachloride?
Yeah, that's it. I was wondering why everyone was silent. Yeah, phosphorus pentachloride. That's it. What about the next one? PCl3.
Phosphorus trichloride.
Phosphorus trichloride, perfect. What about SO2?
sodium dioxide.
Not sodium, what's
Oh. Wait, S is sulfur.
good? Sulfur dioxide. Good. Perfect. And we have some comments in the chat. I'm sure it's all correct answers. And yes, it is not carbon dioxide, but sulfur dioxide. I'm sure that's what you meant. Okay. From the following, systematic names. Okay, so sulfur hexafluoride. What's that? What's the formula for that? Anybody? Good, SF6. Good job. Sulfur trioxide.
It's CO3, trioxide, right?
3?
SO3, sorry.
You said C.
Yeah, sorry.
Okay. SO3. Good job. Good job. So yeah, that's pretty easy. Covalents are a lot easier than ionics. And there's no crazy rules after this. That's it. Those are all the rules for covalents. So we have this flow chart for naming ionics and covalents. So is it a binary compound? By binary meaning, is there one part? Is there two parts? First part, second part. Yes. If there's a metal present, if there's a metal, then you go to the ionic. I hate this chart, but like if there's a metal, if the metal form of more, does the metal form more than one cation? Meaning, is it a transition metal? If it is, then you have to do type 2, which is using the Roman numeral. If it's not a transition metal and it's in group 1A, 2A, or 3A, or the zinc, silver, and if it's 1A, 2A, aluminum, gallium, zinc, silver, cadmium, then you do type 1, which is just use the element name as the cation. Oh yeah. Overall, it's the same thing. Oh, here's for polyatomic ions. If it's a polyatomic ion, if there is, then you just name it with the polyatomic ion. If there isn't, then you just name the... Oh, if it's not a binary, sorry. If it's not a binary and it's a polyatomic, we have that. If it's meaning there's a lot of elements in there that's neither of these, which a lot of compounds are still there. A lot of organic compounds are none of the naming schemes that we learned. It falls into the category which we didn't go over yet. So here's the full slide of the rules. And there's everything you need to know. So on the right side, you have covalent. You notice how short the covalent rules are compared to the ionic? So that's really all you need to know. So yeah. Okay. The last thing that we're going to cover before we do like 5 or 6 examples and then go home. Oh, it's 8:21. We'll do a couple of examples and then after this is naming acids. So naming acids. What is an acid, first of all? So I'll give you some examples of acids. You want to keep the ink on your annotations? No, I don't. So I will share the screen again. All right, so acids. A couple of them. You have HCl, H2SO4, HNO3, another one, HNO2. We'll just name for 2. There's gonna be a whole chapter on acids and bases, but here's some acids. What do they all have in common? Hydrogen, good. They have always a hydrogen in the front. One or more. So molecules in which one or more hydrogen ions are attached to an anion. Chlorine's an anion, sulfate, nitrate, nitrite. So these are examples of acids. Nomenclature rules depend on the anion, or depend on whether the anion contains oxygen. So it really depends on what the anion is. If the anion ends in IDE, the acid is named with hydro and the suffix ic. It ends with the suffix ic. So that's a weird way of saying the only way for the anion to have an IDE ending is if it's one type of element. Chloride, bromide, phosphide, oxide, such as this one, HCl. HCl is hydrochloric acid. Chloride became chloric. Notice if the anion ends in IDE, the acid name begins with the prefix hydro, so it becomes hydro, and then ends with ic. So hydrochloric instead of chloride, chloric acid. So that's that. Does that make sense? Okay. Next is when the anion contains oxygen, oh look, all the other ones, based on the name of the anion, the acid name is formed from the root of the name of the anion, ic or us. So what the hell does that bullet point mean? It means that if the anion, for example, this is sulfate, if it, that's not a, whatever, this is 8. If it ends in 8, it becomes ic. If it ends, and this is nitrate, if it ends in ic. So H2SO4 is sulfuric acid, not hydrosulfuric acid. That's something different. So hydrosulfuric acid is H2S because it has this this IDE. It follows the first rule. So sulfuric, it comes from sulfate. So sulfuric acid is just, you take the anion name, if it's an ATE, make it an IC, and add acid on the back, and that's it. So it's sulfuric acid. No hydro needed. Same thing with this. This is nitric acid. So nitrate, ATE, becomes an IC with an acid. Then you have this one. NO2 is nitrous. Oh, no, it's not. It's nitrite. I just gave you the answer. It's nitrite. So the nitrite, you have an ITE ending. It becomes an OUS ending. OUS acid. So nitrate, nitrite forms nitrous acid, not hydro either. So the only time you're going to use hydro is when the anion is one element by itself, basically. When you use the ICE or the IC, it's when you have an anion with 8. 8 ic. Ite us. That's basically it.
So would it be wrong to say if the anion is polyatomic, as in, does polyatomic refer to number or like different elements?
Polyatomic means number. So if there's more than one atom, doesn't matter what element it is. Yeah.
Never mind.
Okay. So I think you're on the right. I know kind of what you're saying. Yeah. So here's those rules written in stone. If the anion name ends in ATE, the suffix IC is added to the root name, and then followed by acid. If the anion ends in ITE, then you're using ITE is replaced by OUS. So here's some examples of the first type that do not contain oxygen, and then that have just one atom or one. It's really, the real rule is they don't contain oxygen in the anion, because you have exceptions like cyanic. So this is called cyanide. This is hydrocyanic acid. So it's not just cyanic acid. Because cyanide ends in an IDE, technically, even though it's 2 atoms. That's kind of a weird technicality. But the other ones is just 1 atom, a monatomic anion. So you see hydrofluoric, hydrobromic, hydroiodic, stuff like that. Okay, next you have the ones that are either ATE or ITE. So we went over these already: nitric acid, nitrous acid, sulfuric acid. Then you have SO3, which is sulfite, becomes sulfurous acid. H3PO4, phosphoric acid. HC2, and then the CHO 232, which is acetate. So it becomes acetic acid. So acetate has the has the ATE ending as well. So yeah, any questions on that? No? Okay. I'm sure you guys are really exhausted. So we will do a few examples of just overall naming, and that's it. So So those of you who are online, you could answer these two. I gotta, all right, whatever, we'll just do it like this. All right, so name the following compounds. CUI. So do we know the charge of copper off the top of our heads, off of the chart? Is it one of the ones in the, but we do know the charge of iodine. What do we know?
Iodine -1.
Good, iodine is -1. So that means copper has to be +1, good. And copper is in the middle, it's in the transition metals. So our answer would be copper 1 iodide. So really the best thing is when you have a jumbled up list of compounds you have to name, always ask yourself first, ionic or covalent or acid. Once you categorize it, you can go into that naming scheme. So let's go for B. Is it ionic or covalent? S4, N4. And how do you know if it's ionic or covalent? Based on the metal, right? If it's a metal, if there's a metal involved anywhere, it's probably going to be ionic. No metals, covalent. So is B ionic or covalent?
Covalent.
Good, covalent, because sulfur is non-metal, nitrogen is non-metal. So what's the name of it? Weird name. So what's the prefix for 4? I don't know. Everybody's brains are shutting down. It's that time of the day. I taught an 8 a.m. class today, so there's no excuse for you guys. No coffee either. So tough, right? So there's 4. What's the prefix for 4? Online people, you can see the next slide, so you should be able to get this. Oh, now somebody said something. Where's the chat? I can't see it.
Tetra.
Good, tetra, good. Yeah, for some reason the chat's not popping up on my window. Anyway, so I'll do it for you. This is painful. So tetra sulfur, tetra nitride. It's weird, but that's the name of it. So not nitrogen. Nitrogen becomes nitride after you make it the IDE ending for the second one. So there it is, tetrasulfur, tetranitride. Next one, and I give you a hint, HCO3 minus is bicarbonate. So what's that one going to be?
Sodium bicarbonate.
Good, sodium bicarbonate. The last one, this is ABCA. That's cool. So CrO4 is chromate. It has a 2- charge. So what is BA? What is the name of it?
It's barium chromate, or
Perfect. No? Perfect. Not or no. Be confident in your answer. It is barium chromate. Good job. Okay. We're done. You guys are good. Good job. So there's actually 10 more slides here with more questions. You can do that on your own just for extra practice. You're gonna have the homework, which is a lot of practice as it is, and I will post some non-graded worksheets that count also. So I'm gonna stop the recording.